Hi guys, welcome to another one of my lectures, and today we'll be looking at CAPE Unit 1 Module 3 Young's Modulus. Now before we go down the concept of Young's Modulus, I'd like you to remember that Young's Modulus is just like density, it is the property of the material itself. So when you talk about different materials, like you could talk about a piece of glass, you could talk about wires, different metal wires, you could talk about rubber, each of them has a particular property called the Young's modulus. Now the first thing we're going to do is we're going to get this symbol, and Young's modulus is given by capital E, and in its simplest terms it is described as a ratio of stress to strain. Now stress is symbolized by sigma and strain by epsilon. So here these are Greek symbols. So I could simplify an expression for Young's modulus. Now stress, and many times in the exam they ask you to define it, is comparable to the definition of pressure. And it's different to pressure because you don't conceptualize it as the force acting normally per unit area, but you just consider the force acting per unit area. Because many times when you talk about a shear stress in like fluids, when you have different layers moving relative to each other, you can have the force moving parallel to the area. Right, so in general terms, we talk about it as the force acting per unit area. And just like pressure, its unit would be Newton per meter squared, or we could consider pascals. Now, when we talk about the strain, we talk about the ratio of the extension to the original length. So strain is a dimensionless quantity because there are no units. So we consider here to be E over L, right? And we have no units. Now when we talk about strain, right, we can revise a little bit about Hooke's law. So when I talk a little bit about Hooke's law, I'm talking about an elastic body, right? Initially, this body would have some original length. And then when I apply a load to the body, a weight mg, there is some extension, right? And then the relationship was established. F is equal to KE, where the applied force is equal to the spring constant K multiplied by the extension. Now, when we talk about an elastic body, I just want to draw this. You will have a situation arising in a couple of the past papers where you have two springs and they have different spring constant values, because remember K is a measure of the stiffness of the spring, right? So different spring constants have different measures of unit extension. So what I mean is the definition of K is typically F over E. So it is the force required to cause a unit extension on your elastic body. So here I could apply, let's call it deforming force F, right? Now in series, we're going to consider that the force F is applied to each spring, the same force that is. So the total extension is equal to E1 plus E2. But we're going to recall Hooke's law. So if F is KE, it implies that E is F over K. So the total extension will be the force over the net spring constant. That is, if I were to compile these two into one spring, what would be that net spring constant? So that would be F over K1 plus F over K2. Right? So here we are going to divide by F. So I have 1 over the net spring constant is 1 over K1 plus 1 over K2. So therefore you could say it's opposite to two resistors in parallel. Two resistors in series, where it is equal to a resistor in parallel. Alright, so let's consider now another case with two springs. And you have these springs, same thing, but they have a parallel arrangement, right? So here you would have K1 and here you would have K2. So you're assuming here that the force applied, the extension is the same, E. So you're assuming that you would have half the force applied here and half applied here, for example, right? So F is equal to KE. So you're assuming that you have F1 applied here and you have F2 applied here. I had just used half and half initially because you could assume that K was the same, for example, right? Because many times you would say two identical springs. If in an exam you are told about an identical spring, then K is the same. All right. So therefore F, we call this F is F1 plus F2. So K net E is equal to K1E plus K2E, right? So therefore, if we divide by E, K net is equal to K1 plus K2. So in parallel is like equivalent or resistant series, right? So it tends to be opposite to each other. All right, so let's move on now to a graph, right? Because we started off the lecture by talking about stress versus strain. So here, if I have a graph of stress versus strain, right, the gradient, no unit, right? The gradient of that graph can give me the slope of the graph is equal to my Young's modulus. So therefore, if E is F over A divided by E over L, I could say that FL over EA is a final expression for the Young's modulus. Now, when we talk about Young's modulus and different materials, you can look at a force extension graph. I want to go back to that because I want to bring up a point. So if we have a force extension graph and we say that it obeys Hooke's law, it has a linear relationship. Now, when we talk about a body being stretched, there is a release of elastic potential energy, because when the body, that is the deforming force, is applied, it causes an increase in the spacing or the distance between the molecules in that elastic body. And as such, we can look at it as an increase in the elastic potential energy, or you can conceptualize it as like energy released when the body becomes stretched or deformed, right? So here, if I have a force extension graph, I want you to understand that the work done to stretch the body, that is the energy released, is the area under the graph. So typically, if the graph obeys Hooke's law, you'd expect a linear relationship, and that would be a half F by E. Now remember, the maximum point of obeying Hooke's law is called the elastic limit, right? Because beyond that, there is permanent deformation. Now, when you talk about elastic or deformations, we can look at the concept of an elastic deformation. So an elastic deformation is one which obeys Hooke's law, where we say F is proportional to E, and you have the body returning to its original position, and that's most important, right? It returns, the molecules return to their original equilibrium position. Now, when we talk about a plastic deformation, right, we talk about Hooke's law not being obeyed, because in Hooke's law, remember, you say that, right, it's not valid. So the force is not proportional to the extension. So you cannot predict what the extension would be per unit force, right? And also, when you talk about a plastic deformation, you consider that there are planes of molecules sliding against each other, and that results in a permanent deformation. But when you consider an elastic deformation, you have the individual molecules on application of the force shifting slightly from their equilibrium position, but when that force is removed, it returns to its original position. But when you talk about plastic deformation, you're talking about planes of molecules sliding against each other. Now, one of the things you have to learn is the difference and the graphs corresponding to three types of materials: crystalline, polymeric, and amorphous, right? And these would contribute to ductile, brittle, right, and polymeric materials. So when we talk about, let's go with this first one, a crystalline material, we are talking about like basically a metal, right? And crystalline materials are deemed ductile. A ductile material could be a wire, for example. So when we talk about a crystalline material, you are talking about that lattice arrangement. So like before, you would have clusters of molecules, right? And you would have them having a very rigid crystalline material. Now, the concept of that, right, in this lattice arrangement here. So what you would find here in a crystalline material example, a metal wire, is that it would first undergo elastic deformation, and then it would undergo plastic. So plastic is permanent deformation, right? So it would obey Hooke's law up to a point. So if I look at a typical graph of force versus extension, I'm going to get a straight line portion, and then the graph would begin to curve. So this shows that there is elastic here, and this shows there is plastic. And this graph is typically for a ductile material. And when we talk about a crystalline material, the behavior of it is such that when the metal is under stress, you have movement of atomic planes. So you have an initial elastic distortion where the planes are displaced a small distance, right? The molecules, because remember it's a lattice arrangement, so it's sliding on the planes. And if the force is increased beyond a certain value, then the sliding becomes more permanent, right? Where the atoms would move to a new position and they can't return to their original position. Now, the next material I want to talk about is an amorphous material. And these materials are deemed brittle. So when they talk about being brittle, if I have a force extension graph here, then the graph is a straight line, and then there is nothing after that, which means that it would obey Hooke's law up to a point, but then there is breakage, right? So what happens is that if that breakage has occurred, it only undergoes elastic deformation. Now, amorphous materials like glass have what we call a short range order. So when I talk about a short range order, the molecules are arranged in very short chains, right? So as soon as there is a very large force, it results in the breakage of it, right? And you do not have any plastic deformation. And amorphous materials are typically solids or liquids, right? And they do not have a regular repeating structure like a crystalline material. They have a short range structure, which is different to the next type of material called a polymeric material. And you would find that in an amorphous material, if you want to compare it again to a crystalline materials have a regular repeating arrangement, a regular repeating structure. But you will find that amorphous material, the atoms are in a very disorderly arrangement. Okay. Now the last one I want to look at is called a polymeric material. So like the most popular polymeric material is rubber, for example, right? And what you would find is that you have what we call a long range order, right? So when you have a long range order, you have the molecules, you have like real long chains of molecules arranged, and they have a very tangled, if you want to look at it from a very layman's point of view, it's a very tangled, it's like a rope tangling up, right? Now when you apply a force, it results in the molecules having a straight arrangement, a chain arrangement, right? Now you will find, however, that polymers are more subject to expansion. What do I mean? It means that when the molecules are in motion constantly, and they possess a certain amount of thermal energy. So when it is that the force is applied, the polymers can be stretched many times to their original length, right? But you will find that when they are stretched, that is, you would have loading occurring, then you would have an increase in force per unit extension. These bodies do not obey Hooke's law, right? But when you remove the force, the extension again would not be linear. But there is also some energy differences, because the energy that is released when the molecules are being stretched, that is that elastic potential energy, is not conserved in terms of it is converted to some internal energy of the rubber molecules, right? Because you would find that when you keep stretching and releasing them, that they would possess an increase in the temperature because there is an increase in their internal energy. So a typical graph of force versus extension for loading and unloading would be a graph like this, and then the unloading is a graph like this. Now, if you are loading it, you notice that you would have all of the energy loaded is not conserved when it's unloading. And this energy difference here is what you call a hysteresis loop. Right? And that hysteresis loop represents the energy used to increase the internal energy of the molecules, which is therefore dissipated as heat.